ওকে, শোনা যাচ্ছে এবং স্লাইড চেঞ্জ হচ্ছে, তাই তো?
Yes.
ওকে, ঠিক আছে, উই ক্যান স্টার্ট। ও আচ্ছা, এটাকে ও আচ্ছা, এটাই আমি ভুল করছি। দাঁড়াও, আমি প্রজেক্টটা কানেক্ট করিনি, বলে আবার একবার দেখতে হবে। এটা আবার কি চলে এলো এখানটায়? এরকম তো কিছু ছিল না। হ্যাঁ, এটা কেন এলো বুঝতে পারছি না। না না, এটা স্লাইডের প্রবলেম না। ঠিক আছে, না না, দেখে নিচ্ছি একবার। রেকর্ড যদি তোমরা করতে পারো করো, আমি তো এখানেই রেকর্ডিং দিচ্ছিলাম। আচ্ছা, করো করো। না না, রেকর্ডিং হবে, recording হবে। হ্যাঁ, এই এবারে একটু দেখো তো, হচ্ছে, স্লাইড চেঞ্জ হচ্ছে এবং শোনা যাচ্ছে।
হ্যাঁ শোনা যাচ্ছে, স্লাইড চেঞ্জ হচ্ছে, কিন্তু মানে প্রেজেন্টার্স ভিউটা দেখতে পাচ্ছি, ফুল স্ক্রিন স্লাইড নয়।
এখানে তো মানে সেটা আমার স্ক্রিনে দেখা যাচ্ছে ঠিকই, কিন্তু সেটা তো হওয়ার কথা না। এখনো কি একই?
না না না, ঠিক আছে স্যার, স্লাইডটা চেঞ্জ করুন।
ঠিক আছে তাহলে,
একবার স্লাইড চেঞ্জ করবেন স্যার।
করলাম।
হ্যাঁ চেঞ্জ হচ্ছে, হ্যাঁ।
তাহলে রেকর্ডিংটা আমার স্টার্ট করতে হবে। রেকর্ডিং তাহলে কি করব, আমি করব না? দিতে পারি এখানে।
Recording is already there. Who is recording?
রেকর্ডিং দেওয়া আছে, ওকে, ঠিক আছে, দেন উইল। আচ্ছা আচ্ছা, ঠিক আছে। ওকে, এবার start. Let's start.
The pleasure to introduce my long-time friend, Professor Archon Mojumdar. Professor Archon Mojumdar did his MSc and PhD both from Delhi University, and then he has traveled a lot abroad and inside the country. Then he joined SN Bose National Center for Basic Sciences, where he's continuing still with the professor there now. His main focus was and is in cosmology and also quantum entanglement, although I don't know whether he will be talking about quantum entanglement here today or not. But what the title suggests that it will be inhomogeneities in the universe and the gravitational wave propagation. And I have just happened to peep into his next slide, which was Vincent van Gogh's Starry Nights. And so he is going to relate the Starry Nights with the vast universe around. So without much time, I invite Professor Majumdar to.
Thank you, Devashish, for the very nice and kind introduction. Yes, I don't remember. I was trying to remember when we first met. I mean, many decades ago.
In peer
Yes. That was more than 30 years ago.
Yeah.
And since
1991.
Yes. Since then, we have, of course, been in touch in many different occasions. So thank you for the very kind introduction. And I also must thank the organizers for inviting me to here. It is always a great pleasure to be able to speak before young students and interact with them. So let me move to this side. Maybe.
Actually, if you prefer, if you go to that side, because your voice is recorded.
Okay. Yeah, I'm not obstructing this. Okay. So essentially what I'm going to talk about today is about cosmology and unfortunately or fortunately nothing to do with quantum entanglement. That is the other hat I have to wear. But anyway, nothing about that in this talk. And so this talk is based on some works which our group has been doing at the SNBOS Center for the last 10 to 15 years. And I have just listed some works of the last 5-6 years. But the point is not that it's a colloquium talk. So this is just a reference. So I will try to, basically motivate you regarding this area. And it is not essential that I run through all my slides because the main point is to get something across to you. And I would again say that if you have any questions at any time, please feel free. It is, I don't like to give formal lecture. So please feel free to interrupt me, ask questions at any point. Okay, so this, as the title suggests, we are dealing with the universe with large-scale inhomogeneities and the cosmological evolution in the universe and gravitational wave propagation. So why should this subject be interesting? So first of all, I don't know if is anybody a student who is doing cosmology in this audience? Maybe not, but at least you are astrophysicists. So astrophysics has to have to live and study a universe which is evolving according to.
Click on the slide. Click on slide.
Yeah. Okay. So then cosmology is a subject which is fascinating and some people regard it as one of the most fundamental of all sciences. Why? Because universe is only one. It evolves. It evolves only once. There is no repetitive experiment. So during that process of evolution, some signal comes to us, which we have to observe. And if we are lucky or we are clever, we observe those signals, and then we have to make a theory for the evolution of the universe. And of course, cosmology is a well-studied subject. It has been under study right since almost, more than 100 years now. Slightly maybe less the birth of Big Bang cosmology. But there are still some profound questions in cosmology, which I would try to highlight for you to begin to make this area interesting. So first of all, we ask that, okay, we observe our universe. So essentially in a nutshell, what is the nature of our universe? What are the major components of our universe? Of course, we observe the universe from many different physical aspects. We observe light, we observe matter, we observe also different kinds of energy. What are the components and how such components came about? Okay, because it is nobody, there was no experimenter to supply these components to us, but we have to theorize how these components came to us. And the biggest question people ask is, how did the universe begin? And since it is evolving universe, so we are in, that is the most, accepted model, Big Bang model of cosmology. Earlier on, there was also 50 years ago, I don't know, maybe for young people, it is not so relevant, but when we were students, Slightly some decades before that, the steady state cosmology model was also there. And one of the major physicists in India, Narlikar, used to work in that. So there was some question, regarding that. But now it is almost settled that there is nothing like a steady state model. The universe is evolving. So since it is evolving, it must have had a beginning and what will happen in the future, how it will end, or whether it will end, in what kind it will end. So these are the big questions that one asks in cosmology. Okay, so just to, repeat what I've been saying. So universe, how it appears to us, that is in a nutshell. So there are different shapes and structures in the universe, and all of you being astrophysics students are very well aware of it. You study our planets, you study the sun, the solar system. Going beyond that, you study many stars, you study the galaxy, and also go beyond that to study intergalactic objects and scales. Okay. So that means there is structure at various kinds of scales. If you look into the solar system, there is some structure, sun and the earth and other planets are going around it. Solar system is itself going around the galactic center, which is supposed to contain a very supermassive black hole, and so on and so forth. Even the galaxies cluster, some galaxies club together. And if you look into large domains of the universe, there are big voids where there is no kind of visible matter, at least, and maybe not even dark matter. Now, the question is that even though the universe has structures at many different scales, when we talk of cosmology, we talk of the whole universe. And in that aspect, as we know, because this is one of the motivations for the standard Big Bang model, at very large scales, the universe is homogeneous and isotropic. That means if you look into very many, super large distance scales of the order of 100 megaparsec or 500 megaparsec, after that, every side you look, the universe appears to be the same. So that is the other name of isotropy. And from one point to the other, if you move at very large scales, again, I'm talking of scales much, much larger than galactic or cluster scales, the universe appears same to all observers. That is called homogeneity. Now, isotropy and homogeneity are two concepts which were taken into account in the cosmological principle, and from the cosmological principle, the theory of Big Bang cosmology or standard cosmology was born from it. Now we have to study the content and composition of such a cosmology, and evolution, as I said, is an expanding evolution. And again, to repeat, through the observations now, what we can conclude or learn from how the universe was, say, billions of years ago, and what can we say about its future. So these are the questions of cosmology. Okay. And this is a famous diagram, and all of you must have seen it. Nowadays, it also appears in the net, TV shows, everything. Only 2 or 3 days ago, I just looked into the CNN channel. Somebody was giving presenting this diagram. I thought, fine, I will also include it in this column. So it is thought that the universe originated from a point or very small region of space-time in a big bang, tremendously high temperature, high density, approaching infinity, and the universe started expanding very rapidly. So the earlier stage of expansion is called inflation. And although the theories of inflation have been around for the last 40 years, in recent times, there is also some kind of experimental, I would not say confirmation, but at least supportive inference in the form of CMBR anisotropies. Because that is the only time I will use the word quantum in this lecture. So the fluctuations at that time were quantum mechanical in origin. And this led to, because as predicted from the theory of inflation, this led to density perturbations, matter perturbations, and geometry perturbations. And therefore, the CMBR, which got originated, of course, sometime afterwards, carried the imprint of these fluctuations. And if you see the CMBR 2.7 degrees microkelvin in the sky, if you look into very close, say 1 degree differences, there are anisotropies of the order of 10 to the power of -5. Delta T by 2, temperature anisotropy. Okay, again translatable in terms of matter inhomogeneity. So then after inflation, the universe actually settled down, and all particles, all matter is supposed to have originated from the Higgs field or super Higgs field at the time of inflation. Any particle that you see today has origins in that. Of course, that's exactly, we are not still fully, confident about the particle physics model. And my friend was will be able to tell you better regarding this. There are still some controversies, but at least it is thought that all particles originated at the time of inflation. But what happened is the universe exited with exponential, very fast expansion, but it still was expanding, but the expansion slowed down. And for a number of years, and then that period is called radiation-dominated era of the universe. Again, experimental confirmation comes from something like Big Bang nucleus. We won't have much time to discuss it today. But afterward, the universe entered a large period of so-called dark ages, where not very much interesting happened. Of course, there are many things which happened there, but not so super interesting as, say, inflation or radiation dominated. But the universe entered a matter dominated era. And after a certain time, of course, it was still a very uniform, homogeneous, smooth universe at that time. Particles spread around with nearly homogeneous density. But at some point, these structures that you see started originating. Okay, so the first stars were born, and then, of course, 2-3 generation stars were born, but stars clustered together, planetary systems were formed, galaxies, so on and so forth. But what is most interesting to cosmologists today is that even that era has passed, and sometime very recently, at the redshift of, say, 0.6 or something, the universe again entered a state of accelerated expansion. So there are 3 types of expansion. First of all, accelerated in inflation, then decelerated expansion, and finally, at the present era, accelerated expansion again. So what is the cause? What is the reason behind it? Do we have any idea? So that is something which is of most interest to cosmologists. And this was observed by supernova experiments, several groups, starting early 1990s onwards. Okay, so when we were PhD students, the era we were referring to at that time, there was a lot of interest, curiosity, because that exactly at that time, there were large global, multinational experiments which told us, supernova experiments, that the redshift is such that we can now know that the universe is accelerating at present. So this is the universe in a nutshell. So where do we come in? So this is the observational part. Now, the theoretical model to describe the Big Bang theory, expanding universe, is supplied by nothing else than general theory of relativity, and it is a metric theory in terms of the metric tensor G mu. And of course, the general theory of relativity has to conform to certain principles like the equivalence principle, and it brings about its own symmetries. And now, essentially, what happens is that one applies the Einstein equations to the whole universe, right? So that is something, please keep it in mind, because it will be important when we come to the next slide. And of course, to you people, I don't have to say what this means, Einstein equation means, but that is a statement for a layman. So this left-hand side is geometry, right-hand side is all the matter and energy. The geometry tells matter how to move, and matter tells space-time how to curve. So this is the content of general theory of relativity, which all of you are aware of. Now, the standard cosmological model can be derived from this Einstein equation by assuming 1 or 2 things. First of all, as I said, it assumes the cosmological principle, that is, there is isotropy and homogeneity at large scales. And using that, and also the energy momentum tensor, this thing that was on the right-hand side, T mu nu, we have to keep its symmetry matching with the symmetry of the left-hand side, right? If the left-hand side space-time is homogeneous and isotropic, the energy momentum tensor also has to follow the same symmetry. So therefore, what kind of energy momentum tensor fits that? It is the energy momentum tensor of a perfect fluid, which is just labeled by 2 objects, the energy density and pressure. Okay. And once you do that, once you substitute that in Einstein equation, you get the dynamics, which is described by the so-called Friedmann equation. And this is the Hubble tensor. A is the scale factor of the universe, which tells us how the universe is expanding. Okay, right. And you have 2 equations. One is the first derivative, the other is the second derivative. So these together, once you supply the energy conservation equation and certain geometrical constraint, this describes for you the cosmological evolution in a nutshell. And this is a theoretical model, but that today we call it the lambda CDM model, because lambda CDM is something which takes into account both the early evolution as well as the current accelerated expansion of the universe. which is also, some people like to call it dark energy, and that can only happen, such accelerated expansion at the late stage. It can only happen if there is some exotic energy content, and that is called dark energy. That also can be modeled by a cosmological constant, which was famously introduced by Einstein and retracted, but let us not go into that. But today there is observational support for the lambda CDM standard model of cosmology from many different observations. So 3 of them have been plotted in this diagram. One is the supernova observation, which I was talking of. The other is the baryon acoustic oscillations, okay? And finally, the third one is the CMB observation. And all 3 actually overlap at a certain region, and this is the omega lambda, omega m. What is omega lambda? Omega lambda is the fractional energy density in the universe, which is caused by the cosmological constant lambda, or dark energy. And omega matter is the fractional energy density in the universe, which is supplied by all the matter content in the universe. Both that you see, that is visible matter or standard matter, as well as dark. So in this plane, all 3 observations actually overlap at a certain point, and what it tells us that at present, the major fraction of the energy density content in the universe, it is dominated by lambda or dark energy, that is around 0.7, and rest is matter or dark matter, 0.3. Okay, so this is the content of the universe, and funnily enough, we live in a universe whose contents we know nothing about. Okay, because the visible matter that you see, all other things, I mean radiation, all baryon particles, etc., that you see today constitutes less than 2 or 3% of the universe. The rest of it is dark matter, and of course we have several theories behind dark matter. Dark matter is, at least in the sense, it has got some, I mean, pressure or no pressure, whatever it has, but it is less exotic compared to dark energy. Dark energy is something which has got negative pressure. So have you ever come across anything that you know which has negative pressure? Yes? I don't think so. So dark energy is so mysterious. Okay. But without negative pressure, there cannot be any accelerated expansion of the. Okay, so this is the part. By the way, I mean, I'm going slowly. So tell me when I need to stop. Because
I'll give you a 10 minute.
yeah. So there is no kind of hurry. And if there are any questions, please ask me. So now the perspective behind our work, our entry, this is all general knowledge sort of that I've given you, starts now. And why we are interested in studying this area, what exactly we study in this diversity, is that we look into cosmology, that is late time cosmology, which is, I mean, one from the study of which one knows that the present universe is accelerating. And we have a number of observations today, satellite-based observations, ground-based observations. That is why we say that we live in an era of precision cosmology. And we can precisely determine the observable parameters of the universe. For example, the Hubble parameter. We can very precisely determine. Okay. And this is based, of course, we know the universe is accelerating, but this is based on something which is called dark energy, and it also requires dark matter. So those of you who have studied particle physics will immediately know that in standard particle physics, we cannot talk of such, dark matter to say, not baryonic dark matter to be precise. So one has to go beyond the standard model of physics. Even in the neutrino sector, one needs mass for neutrinos, which in the standard model, there is no answer. Okay. And of course, this is the cosmology we understand today, but those of you know there are some unanswered questions there also. For example, I was talking of the Hubble parameter. We can determine it through 2 different observations. One has to do with the present acceleration, the other has to do with CMB physics. But both give slightly divergent values. So there is some tension. There are some questions. So people will argue definitely that Big Bang model has tremendous sound footing observation, but there are some questions still remaining. So that is one thing. On the other hand, the main motive for our works in this area is something else, that though the universe at very large scale is homogeneous and isotropic, it is thought to be homogeneous and isotropic. And so far we can look into the sky with our telescopes at very large scales, it seems to be homogeneous and isotropic, but there are still evidence of some structures present at extremely large scales. For example, something like 500 H inverse megaparsec, and there is a giant arc which has been detected. The arc range is about 1 gigaparsec. So it is a huge structure. Okay, and we know that there are some inhomogeneities in the universe. So these kinds of objects we call inhomogeneities. And this has been discovered in very recent years. Okay, not too many years ago, and more of such things are being discovered. The presence of large-scale inhomogeneities, which are there at extreme structures, which are there at extreme large scales, and also there are certain regions of the universe which are very large voids. Okay, nothing is there. So now the question is that the Big Bang model is based on the assumption of homogeneity and isotropy at very large scales, which does not take into account the presence of such inhomogeneities. So will such inhomogeneities play any role in the evolution of the universe? That is the main question that we ask. Okay, is the motivation clear? That is the main question for this talk. And another motivation is because the standard lambda CDA model is based on at least 2 or 3 things like dark matter and dark energy, for which there is little observational support. Okay, dark matter has not been directly detected. Many people believe that, and dark energy is not even understood at the theoretical level. So can we do without dark matter and dark energy? Is there any way out? Okay. So one of the possible ways could be the presence of such large-scale structures, which can give us a hint that their effect, if we properly take into account, might be able to explain the evolution of the universe, present evolution. Okay. And also, again, to emphasize, we live in an era of multi-messenger astronomy. So not only do we observe light like CMBR from very early times, but we also observe gravitational waves. We also observe something which is called the 21 centimeter signal. Maybe towards the end, I will come to it if time permits. So therefore, this leads us to, as I was saying, precise estimation of parameters concerning not only evolution of the universe on large scales, but also some interesting objects that you see. For example, in the last few years, systems of binary black holes have been detected, and gravitational waves have been detected from them. There are two big conglomerates, LISA and LIGO, not LISA, LISA is coming up, LIGO and Virgo, which have detected the gravitational waves. Now, using those detections, people try to model these large compact binaries. They can be black hole, or neutron star, whatever. They try to estimate parameters. Okay. Now, does this kind of, evolution of the universe, or evolution which is predicted in a slightly different way due to inhomogeneities, what can they tell us about these object parameters? That is one more question that we ask. Okay, so let us move on. So this is just a repetition. This is the Friedmann-Lemaitre-Robertson-Walker model. So the universe is homogeneous, no preferred location. Every point appears to be the same as any other point. Matter is uniformly distributed, and isotropy means no preferred direction, and also no large-scale flow of matter from one point to the other. And this is the content of the cosmological principle, which is thought to be observationally valid at very large scales. Again, to repeat, recent observation, for example, Sloan Digital Sky Survey and because the Dark Energy Survey indicate that although homogeneity may exist at super large scales, there is transition from homogeneity to inhomogeneity at very large scales of the order of 500 H inverse megaparsec. And that is a big thing. And why is that thing important for the study of cosmology? So this is our outlook. So, for example, again, I think this is repetition of what I've said, but just to tell you, students, emphasize once again, cosmology, as we understand, is very well described by spatially homogeneous isotopic model, modulo some recent tensions, observable Hubble and XZ tensions, but such observational concordance comes with a price. More than 90% of the energy budget of the present universe comes in forms that have never been directly observed, directly detected, dark matter and dark energy. Dark energy is not even theoretically understood. So therefore, there is scope for some alternative thinking, and people have been doing such alternative thinking. For example, people have tried to modify general relativity at large scales. Okay, extending the standard model, or people have said, argued that GR is correct, but the way it is applied to large scales need to have a relook at. And this is one approach, the last one, which is actually following from that what I've been saying, and that is nothing but the effect of inhomogeneities, or do these inhomogeneities have a back reaction on the spatial geometry, and can they modify the evolution of the universe? Okay. So that is the content, and then if they are able to modify the evolution, it will lead to remarkable differences, not only in the whole physics of cosmology, but also to gravitational wave parameters. So that is the outcome. Okay.
These are not stochastic evolution.
No, not necessarily. Stochastic can also be there. This can be part, but I'm not going to talk of stochastic. But stochastic gravitational waves will come under this value very much, because stochastic waves are those which are originated at the earliest point in the universe.
Yeah.
But now, if the evolution of the universe changes, so their amplitude will be there. So they will also come under this form of study, contribute the most. So for example, in stochastic gravitational waves, if you detect them, then you will be able to pinpoint precisely the parameters during the inflation period, inflation time. So the way their amplitude and other properties will govern a large role in that. But if their evolution changes, if the middle evolution, interim evolution of the universe changes due to inhomogeneities, then they will be in that. So they are also in. Okay, so now we come to the heart of the matter, what I've been talking about, what I'm trying to describe. So that is the application of general theory of relativity to cosmos. Once again, that is why I gave you the original slide. So this is the Einstein equation, left-hand side is geometry, and I've also included a cosmological constant, which can be there or may not be there. The right-hand side is the energy momentum. Now, when we talk of cosmology, we take the whole universe into account. So, for example, left-hand side means the geometry of the whole universe. Okay, we do not talk of any structure there. It is the geometry of the whole universe. For example, inside the solar system, we know that the Earth moves around us. Inside a galaxy, we know that our solar system moves around the galaxy. But this has no effect or plays no role in the overall cosmological dynamics, right? Overall cosmological dynamics means that the universe is expanding. It does not mean that the Earth is moving away from the sun. It does not mean that the solar system is moving away from the galactic center. But two galaxies located far apart in space are moving away from each other. Because why? The background space is expanding, right? So therefore, what does it mean? So effectively on the right-hand side, when we talk of the energy momentum tensor, what is the energy momentum tensor of the universe? It contains everything in the universe, all matter, all energy, everything. So you cannot exclude out certain components from it. You cannot exclude out galaxies. You cannot exclude out any other forms of dark matter. So in essence, what one does without stating in so many explicit words, is that we are taking an average of the total energy momentum tensor on the right hand side. So this is very important in the study of cosmology. This is not highlighted. But in effect, in essence, in spirit and in practice, we are taking the average of the energy momentum. But this is a mathematical equation. You see, this is also it is assumed to be ideal fluid, but when you do bookkeeping, that ideal fluid will also contain components of all matter, all sort of not only dark energy but dark matter, anything in it. And those may not be uniformly distributed. At least matter is not. We know that. Visible matter is not. Even dark matter is not so uniformly distributed. So we are taking in principle an average on all. Okay. But as I was saying, this is a mathematical equation and a nonlinear tensor equation. So if you are doing correct mathematics, you cannot only get away by taking average of the right hand side. You have to take average of the left hand side also. So that is a very big thing which is not taken into account in standard cosmology. So therefore, in order to do correct physics, you have to take in account the averaging of both sides. So the correct equation should be average capital G mu nu, which is the Einstein tensor, equal to average T mu nu. But note one thing, because of the nonlinear character of this equation, the average of G mu nu is not the G mu nu calculated over average of the local metrics. And what are these local metrics? These local metrics can belong to any scale. It can be solar system scale, it can be galaxy scale, it can be cluster scale, so on and so on. So it is a sort of discrepancy, at least in principle, very big discrepancy. In practice, how much it contributes, that is a matter of question, that is a matter of study. So to say it in words, the Einstein tensor constructed from the average metric tensor will not be the same in general as the average of the Einstein tensor of the actual metrics, right? So this is a problem. Everybody can appreciate this problem, but how about handling this problem? What does one do to handle this problem in the study of? So one can try to construct averages of the left-hand side in different ways. And one of the ways is to follow hierarchy. Okay, you first of all take the Einstein equation and apply it to a local level, right? A local, any kind of dimension you can choose. This is a local level. Everything is local here. And you also take the energy momentum tensor of the local level. And in the averaging process, say, go from local to galactic scales to large scale structure scales, so on and so forth. Similarly, also, you could take this energy momentum tensor and go on hierarchy. But the important point to note here is that this kind of averaging process will not commute with the evaluating the inverse metric. For example, if somebody has given you the distribution of matter and from that you want to calculate the local inverse metric at some point, this will not agree. Why? Again, because of the non-linear nature of the Einstein equation. This is simple. You can write down and convince yourself, write down the equation. So typically what will happen is that, so suppose if you want to go from, say, local to galactic scale or vice versa, say from large scale structure to galactic scale, write down this left-hand side from the galactic scale. The right-hand side will typically contain an extra term, which results due to such averaging, okay, which I have labeled by term E. So typically in general, this is not zero, right? So then what will you do? So then in the study of cosmology, when you apply Einstein equation to the standard Friedmann equation, you have to take into account such an extra term, or in the other word, this kind of averaging as a consequence, the Einstein equations, which is valid at local scale, we know from experiments, it is indeed valid. When you extrapolate it to galactic scales, then you have to take into account this correction. Okay. Let me be very clear. General theory of relativity, no problem with that. It is an extremely correct, exceptional theory. Only thing, the way we are applying it, way we are extrapolating to large scales, may not be the most correct, at least in principle, that appears. It may not be the correct method of way we are doing cosmology.
Can we be on consequence of the fact that the equivalence principle is
see, equivalence principle leads to some different elements. So far in all this, the thing, equivalence principle is taken into account. So there is at least the weak form of the equivalence principle is taken into account. So even this business of doing average, whether you do it at large scale or small scale or don't do it, at least equivalence principle is assumed to be valid. But of course, on top of it, if you put in another element that equivalence principle may not hold, that will lead to even more exotic. So far, we are considering it to be. Okay, so then what do people do? So therefore, there are, people appreciated this problem. In fact, almost as early as the time we were again talking more than 30 years ago. And the Zelaletdinov was the first person who tried to handle this kind of averaging in cosmology, which is a theory called macroscopic gravity. But we won't go into that. There have been other. This approach is extremely complicated and difficult, so it did not make so much progress. And there are other approaches also, for example, approaches by Clarkson, Kolb, etc., which use perturbative schemes. Okay, at every point, every scale, you write the perturbation of the metric and the perturbation of the Einstein tensor. But then the most well-known or most widely used scheme was proposed by Thomas Buchert, a French physicist, and collaborators, again here the year 2000, 2001. And these have to do with spatial averages. I'll be talking of that. So in this sort of talk, we will follow this approach. But just for the sake of completeness, I might also say that this uses averaging on spatial hypersurfaces. But in relativity theory, you can also use other kinds of averaging. For example, you can do like cone average. So that is also another method.
But this one we apply for evolution of homogeneities, no?
Yeah, the special, yeah, that we do. So that is the traditionally most used method. Of course, from a strictly a point of relativistic dynamics, there are covariance issues. So that one needs to handle. Covariance issues are there, but as long as we are talking in the classical domain, that is late time universe, such covariance issues don't play a role. Only in the early universe, when quantum physics is important, such covariance issues may play a role. But anyway, so we are talking of averaging over structures. So in the early universe, there is no structure.
Yeah.
So therefore, such issue is not important. Okay, so these are all top-down approaches, okay, but there are also other bottom-up approaches also, which we will not have time to discuss. Okay, so we confine ourselves to the Bruckert framework, and essentially, so this is the colloquium talk. I will not, bore you or tire you with too many mathematical details, but anybody who is interested can also get in touch with me after. But essentially, what is assumed here is that the universe is modeled, at least the structures are modeled by irrotational fluid or dust, which is pressure free, and the space time is divided or foliated into constant time hypersurfaces or spatial hypersurfaces, and then you define your metric on such a hypersurfaces, and therefore, so in general, Gij, which you took to be smooth and homogeneous for any cosmological study, in this case, it is in at least to begin with a priori inhomogeneous. So now you take one particular spatial domain, let us say, and then you define everything with respect to that spatial domain. And this is the metric, this is the measure. And in that domain, you define a scale factor corresponding to that particular domain. So this is not the scale factor of the whole universe. So this scale factor is actually, it is what? Because it is inhomogeneous. So scale factor contains information about all the directions the universe may be expanding in different. So this is the framework, and again I'm saying if there are any issues, please ask me later. But since I need to move on, I'm not spending too much time in explaining this. But once you do this, and then what is the main point? We are talking of averaging. Okay, so on this particular domain, you take all scalar quantities and take their average. Okay, this particular. So F is a scalar quantity, and its average on the domain D is given by this, with a normalization over the whole volume of the domain. And once you do it and you then apply it to the Einstein equation, then what you get, you retain the form of the Einstein equation. So this is the second derivative and first derivative term, Hubble's equation. Only thing you collect, first of all, there are, instead of standard quantities, you take averages, domain averages of energy domain density, domain averages of the richest scalar, okay? In addition, you also pick up a term which I have called QD, and that has come about due to back reaction because of this averaging procedure. Exactly in the way I was talking in the last slide. And for technical reasons, we also take into account the integrability condition, that is no major flow of matter from one domain to the other. So that should be taken into account. Okay, so then what happens? So again, this is rho is local matter density, R is richest scalar, everything is standard notation. Now HD is the domain dependent Hubble constant. Okay, or I shouldn't say Hubble constant, I should say the Hubble rate, because Hubble evolved. And the back reaction, which is also in certain parlance called kinematical back reaction. How is it defined? I wrote it down. It has presence in all the Einstein equation. It is defined like this, okay? Theta square average minus theta square, okay? Minus average of theta, okay? Minus sigma. So sigma is the shear. So let us forget about shear for the moment to simplify matters. So if last term drops out, what is theta square? What is theta? Theta is A dot D by AD. So that is the Hubble parameter. You take square of the Hubble parameter, average it. Okay, minus average of the Hubble parameter, domain dependent Hubble parameter, and square it. Okay, so you get the back reaction. Now this can lead to some very interesting effects when you study cosmology. Okay, and how do you study cosmology now? Now you remember that we are in a universe which at smaller scales it is inhomogeneous, at very large scale it is homogeneous. So you take a global domain. Okay. Now you go to a global domain, which is, say, imagine it is very large. So overall it is homogeneous. But now inside the global domain, there are small domains, some of them have with various energy density. Some of them are very dense, some of them are less dense, going on to void. Okay. So you take some elementary spatial entities, FL alpha, you take a union, these are non-overlapping, okay, and similarly for the domain, you take a union of all these F regions, and of course they are not overlapping, so intersection is 0. Now, when you want to calculate the global averages, you have to split them into averages on the subunits. Okay, so that you have to do, so that is the technical part. Once you do it, then what you end up ultimately you have to calculate, you have to solve the cosmological equation, Friedmann equation in the scale modified due to presence of back. So that is the ultimate term. So what is the ultimate term, ultimate modification to the cosmological equation? That is given by QD. So
reaction was QD, right?
Back reaction was QD, back reaction. So what this process leads to this kind of expression for QD, and now note the interesting feature. So the first term on this expression is a summation over all QLs, and QL meaning back reaction over individual QL. So you can set that to 0 also, because you can take the individuals by some approximation. You can take the individual small domains to be overall homogeneous. So you can take their small regions, let us say homogeneous. So then this splits up. So the most interesting contribution is from this one, and this is the cross term, okay, difference between the Hubble expansion rates of two domains. Okay, so let us say L1 and 2, let us for simplicity. One is one domain, which is very dense, and say this one is very light domain, which is say very rare, okay. So they will evolve at different rates, right? Now the Hubble rate will be different. So therefore, there will be a finite term, and this is also square. Okay, so there will be a finite positive term due to differential evolution of two different domains. For square, it will be positive. The why that is important, it will be visible in the next slide. But just keep in mind, just because the two different domains are evolving differently with respect to each other, they give rise to a positive contribution to the back.
10 minutes.
Okay, so I must hurry up. Okay, so now the most important thing is, now let us simplify matters. Let us talk, say the universe has only two domains, one very dense, one very rare. So one is called the ball with over density, and another is called the void with under density. And you do the same exercise, you end up in this Friedmann equation with second derivative, and this is the Friedmann equation and second derivative. And as you saw, if you remember from the last slide, it has QD term. The back reaction is HM minus H. Now just look at this equation. So this is A double dot T, okay? And if you have standard matter, there is nothing like exotic negative pressure. So then A double dot will be what? It will be negative. So for individual domains also A double dot will be negative. But due to the differential rates, it will become a positive quantity. So that energy can, in principle, arise from such a kind of back reaction. In principle. So this is one of the messages that I wanted to give you. But since I am running out of time, so now I will just hurry and show some results. So what we actually, I am one of my students that is very old, actually, more than 12 years ago. We took such evolution into account, the Booker model, and tried to see that the universe, we tried to take the observational facts into account, that the universe is accelerating at present. But suppose this present acceleration goes, forward, if we evolve our equations, back reaction equations, forward in time, what will happen to the evolution? And that is something very interesting. We started from different initial conditions, labeled by the different colors of this graph. And the star points means that at the present day and age, we precisely take into account the present observation. That is the Hubble parameter and the acceleration. And then try to evolve the equation forward. And we see that in all cases, this acceleration dies down. Okay. So what does it tell us? The back reaction Whether or not it can give dark energy, at least it will stop the big rip problem. You know the big rip problem, some of you know that if the acceleration continues forever, then the universe will fly apart. So we will all encounter a sort of a cold death. I mean, nothing will remain, everything will be separated, but at least this back reaction is able to account for that. So the universe will again come back into decelerating. So then we also improved the model. So earlier model was a very oversimplification. I don't know how to go back. Yeah, this one. So for the initial domains, we assumed a power law evolution. There are only two types of domains, that is dense and rare. But if we actually try to improve the model, and for the dense domains, we take into account the closed form of it. Because something which is dense, after a while, it can cut off from the universe expansion and fall together. Right? For example, you also see that the galaxies internally are not moving away from each other. They form a sort of closed loop, sort of. So we took that domain, and then we also did the same study there. And what we did, again, I'm not going to too many technical details. We again solve the equation. We study this. This is forward evolution, T by T naught. So T naught is present time. We start at 1. And for a wide variety of initial conditions, you see that the acceleration, it is accelerating now at present. So it is positive. Okay. But after a certain point, it will rise and fall. Many different kinds of initial. So that is what we got. We got a decelerating future evolution. And this work has been carried on in many ways. But of course, the point is that now that we've got a model, but we also have to match with observation. And what is the best way of matching with observations? What is the most widely, I mean, you people may not know, but the most widely studied dark energy models in the literature in the last 20, 30 years are scalar field dark energy. Okay. Our model does not have a scalar field, but due to its structure, we can map it into a scalar field. Okay. So, mathematics. So what is the scalar field? We write down the Einstein equation, and we write down the effective energy momentum tensor, and then we map it to a sort of scalar field model. And scalar field models have many wide advantage. Why? Because they can be linked directly to observation. Okay. So let me again not go through these details, but what is the analog scalar field cosmology? So if we write down the effective the energy density and effective pressure, then it exactly turns into a wave which is given by a scalar field, which is called a Morphon scalar field model, which has equation given by this. And for such a scalar field model, we can study the dynamics of the effective field potential and the omega, okay, and all the other interesting quantities. And we get back something which is called Thawing quintessence. Thawing quintessence. Some of you are aware, you can read that. And when we can also do data analysis of these models, so we can take supernova data, DO data, and same shift parameter, and we can calculate these so-called statistical parameters. So, for example, this delta resembles departure from the lambda CDM model, and this kind of back reaction model actually compares favorably with certain other modified reactive. So I think 5 minutes if I have. So I will shift to something the last part. Okay. So as I was saying, so this is again something which is we took an oversimplification. We talked of 2-scale model, but we can take multi-domain model as in the universe is supposed to be. Okay. There are many different kind of voids and balls. And what we took is a Gaussian distribution of these profiles, volume fractions. And for a Gaussian distribution, we also studied the same problem. So again, we find that there is no big rip, okay, for a multi-domain. So 50 domains, 100 domains, how many you have. And beyond a certain point, actually, there is no. So suppose from 100 to 500, there is not much difference. So universe with 100 domains is able to sort of account for what we know. Okay, so again, we can apply observational constraints. This is Bayesian analysis using these unions 2.1, but let me not go through into it. If anybody has questions, I will answer. But the last 4 or 5 minutes, I will talk of something else. So far, I was only talking of evolution of the universe. Now, what else can we gain or learn from using such back reaction models? And that is, there are 2 different things actually, because what we see today is something also which is called by the 21 centimeters, which arises from the transition due to the hyperfine splitting of the ground state of the hydrogen atom in the early universe. And it comes with an emitted spectrum, but due to evolution, this is redshifted. And what we find is that the signals that we get for this 21 centimeter is something which is on one hand predicted by lambda CDM, but very recently there was some experiment which is called the Edges experiment last 2 or 3 years ago. What they observed is a tremendous dip in the temperature of the 21 centimeter compared to what lambda CDM is supposed to observe. And using such a back reaction model, this dip can be explained in the 21 centimeter. Again, after the Edges experiment, there has been another experiment called Saras experiment, which did not find any such dip. But at least this gives us yeah. So there are some controversies, but at least using such a model, the main idea is that once as I was talking to Devashish at some point in the lecture, once your evolution is impacted, Hubble evolution, so everything which comes to you from very far away is impacted by the evolution. The 21 centimeter signal is emitted way back in the universe, okay, at a redshift of, I don't know, forgotten, around, I think, 27 centimeter, 21 centimeter, for example, you observe what is going on at the redshift of 17 or so. But the origin is even far back. Origin is even far back at the time of reionization. Yeah. So the universe evolves in such a way, if it is different from standard Hubble evolution, due to back reaction of inhomogeneities, all parameters will be affected and therefore the 21 centimeter temperature. Right. And in the last 2 minutes, I think I've got to the end, but I must talk about this gravity waves, because gravity waves is another way of observing the universe from a long time away, because we know that there is light in the universe from CMB, but if there is some sound in the universe, this is a popular representation, it comes from gravity waves. Okay. So what is the status? Several detection events of compact binary mergers since LIGO and Virgo, and observed GW parameters are crucial for inferring source parameters. That is, what is the mass of such compact objects? What is their merger rate? So on and so forth. And multi-messenger astronomy actually opened us a new observational window to physics, a very interesting thing, black hole formation, say neutron star formation, exactly, and so on and so forth, and many aspects of the early universe also. And the present observation of gravitational waves comes from sources that are well within the scale of inhomogeneity. Remember, when I said that the scale of homogeneity sets it at greater than 500 H inverse megaparsec, certainly greater than 100 H inverse. But all these we are discovering today, gravitational waves, are coming from objects which are well within that, less than that. Okay. So it is inhomogeneous, right? So therefore, the evolution that we talk of cannot be just standard cosmological evolution. There has to be some account of back reaction. Okay. And that is what we actually did. And we applied again this simple 2-scale model. And we, first of all, we studied, because light is also coming from those sources in some cases. We studied light propagation from those sources, and something interesting which we observed, which is called redshift drift. But anyway, we have no time to go through that. Let us come to gravitational wave amplitude. So the gravitational wave amplitude from typical binaries that we get. So this is the cross polarization term which I am writing. The cross polarization is also similar. And what we have plotted is the redshift dependent amplitude of gravitational waves normalized by the luminosity distance. Okay. And this is plotted versus redshift. So it goes like that in various models. Lambda CDM here, somewhere here, orange line, and the other curves are all back reaction model with different parameters. So now it is up to future observations to see where exactly, and all these figures have a minima. Okay. All these figures have a minima. So at exactly what redshift with this minima comes will tell you which model nature is following. So in future, if our observations are very precise, we will be able to have some insights, whether the lambda CDA model is correct or whether such back reaction model is correct, if so, with what values of parameters.
This is the largescale.
Yes. Yes. Okay. So I'm come to the end of it. Actually, that's what I was trying to say, that the actually this minima varies. And this is the input of our work, because some years ago there was this PRL paper which actually claimed that in standard cosmology, this minima will be independent of all binary characteristics, all cosmological model, but they did not take into account this evolution, modified evolution due to back reaction. We have showed that if you take into account back reaction of inhomogeneities, then this minima will vary, and this will open up a window for observational detection or falsification of something. So this is the last slide, summary slide. So I've been trying to convince you of, how interesting the study of cosmology is today, mainly due to observations ranging over a large number of years. First of all, we do have a handle that our universe is expanding. It is also accelerating at present. And a model is used to describe the accelerating universe that has some problems both from the theory side, that is dark energy and dark matter are not understood, not detected, and also something from the observation side that at very large scales there are inhomogeneity. It is not completely homogeneous and isotropic at all scales. Okay. So we studied the effect of back reaction due to inhomogeneities, and mainly our focus was on future evolution. So we took the universe as what it is from observations and put those data in our evolution equation and saw how the evolution will be. And the global homogeneity scale impacts the role of inhomogeneities actually, which causes the acceleration to slow down significantly with time. And back reaction could be responsible for a decelerated era in future. It could avoid the big rip, okay, and such avoidance is possible, but for not all parameters, for a narrow region of parameters. And then in order to map with observations, we could study it in the form of analogous scalar cosmology, not real scalar, but analog, okay. And then we could use observational constraints to use our observational data to constrain our parameters. We also did some other studies in multi-messenger astronomy or cosmology, like 21 centimeter signal, and we could account for the edges result. And finally, something which I did not have much time to talk about, but this is this such back reaction leads to a different evolution. Now, from the observed gravitational wave amplitude, etc., we try to infer the parameters of compact objects and binaries. Those inferred value of parameters undergoes the change. Okay. So this leads to modification of binary gravitational wave parameters due to back reaction from inhomogeneities. And the clear signature is in something called redshift drift. And this is very significant in multi-messenger astronomies, because from the same object, you are sometimes seeing light as well as gravity. Okay. So this is not the end of the story, of course, because so far we have mostly talked of toy models. There are more complicated, more realistic models, and models where we need not make any ansatz for subdomains like closed or power law, etc. And also there are other schemes of back reaction. So if something has to be studied in full glory, we cannot neglect other schemes of back reaction also. We have to see which scheme fits the observation best, because after all, cosmology is an observation. Thank you very much for your attention. If you have any questions.
Okay, so let me first check if there is question from the online. Is there any question from the online audience? Is there an online audience?
Is there that's a good
Well,
That's
I
a-
can ask one.
Yes, yes, please.
Yes. Am I audible, correct?
Yes.
So about the 21 centimeter signal, you are explaining the ages result. It's if you want to see a deep in the 21 centimeter signal, you have to either change the gas temperature or the CMB temperature. So which one in your model is changing?
Yeah,
Gas
that's a good
temperature
question, but
or
that
the-
is yes, I understand. So if you want to see a dip in the 21 centimeter temperature, once you are within the context of standard cosmology, only two things are the two things are responsible, whether your baryon temperature or CMB temperature. That was the question, right?
The gas
Yes.
temperature or same?
The gas temperature. Yeah. No, but every temperature is being redshifted. That you understand, na? Because it is coming from object which is far away, and the universe is evolving, right? So in this case, in our case, the change is being caused just due to the modified evolution of the universe. Change beyond the lambda CDM is just being caused due to the modified evolution of the universe. So in the figure that I showed you, for example, if we come to this figure, for instance, so if you look into this figure, you see I've also plotted lambda CDM here. This is the dash lambda CDM. So for lambda CDM, I'm using the same value of gas temperature and your this photon temperature as I'm using for the back reaction model. So why is this change happening? This is happening because the evolution changes leading to different redshifts for the temperature. So am I clear? Do you get it?
Okay.
But both temperatures are not affected similarly then.
Both temperatures not
Because
affected.
then there will be no dip.
Yeah, of course, but the difference is there which causes the dip. But here the main point is that the same values of both temperatures I'm using for the lambda CDM as well as the back reaction model with different values. Then why is the dip? The dip is due to the redshifting due to modified evolution.
But lambda CDM, you will agree with the 21 centimeters.
Okay, thank you.
300 minus 10.
No, lambda, that's why the ages result gave you a minus 400 degree.
Minus 300 to minus
Not 400 degree. Lambda CDM is did not.
Okay, other questions? Yes.
Now the like basic surveys hinting towards a scenario where lambda CDM is lambda is not constant throughout the so lambda is evolving. So does this formalism will this formalism also be able to explain if lambda is not, if there is a double parameter?
See, in principle, this formalism has nothing to do with lambda. Okay, because in principle, the main motivation is let us start with what is there observed in the universe and let us try to model. Of course, but it is questionable whether it will give rise to the known form of dark energy just by itself. Okay. So now the question is, recent observations say that even the accelerated expansion cannot be modeled by a single parameter lambda, it has to be evolved. So what is the effective theory of lambda? Of course, there is a possibility that back reaction will provide you with a theory. So that is in the general spirit of back reaction. But my talk has to do with even a smaller domain. In that, I am saying that let us take into account what we know observation. If lambda is evolving, let us take lambda as evolving. And then based on that, let us see how the back reaction will evolve the parameter. So we can go two ways, it will go forward or we can go backward. By going forward, we can predict how our universe, what it will do in the future. By going backward, we can do three different things. First of all, we can constrain the model, take into account other known observations, and also we can try to study things like gravitational wave propagation, propagation of 21 centimeter signal. So, but the whole spirit of back reaction is that even say there is no dark energy, can you account for acceleration? So that is debatable. I mean, so far there has not been a very nice, perfect model which you can explain.
Okay, other questions? Yes.
স্যার বলছি আপনি যখন ওই এফএল ডিফাইন করছিলেন
কোনটা?
এফএল টু ক্যালকুলেট দ্য ব্যাক রিঅ্যাকশন কিউ I mean can you little bit explain?
Okay. Let us go back to the mathematical slides. This one or before? That one. Yeah. So these are just regions. So this is a label of regions. This is one region. So one such region. So this is, just think of hierarchy. The smallest thing is FL alpha. Smallest subregion. Take a combination, take a union. You form another.
No, I mean what is FL alpha?
It's just a region, nothing else, a region of space-time. Region of space-time.
So F is what? F is
A region,
any quantity.
rotation. It's a no. It is labels the region. It is not even a physical quantity. Label. It is a label of because F does not appear anywhere else in the equation. F is just a way of labeling the. All that appears in the equation is these scalar quantities which we average on. For example, this F, small f, is any scalar quantity like energy density that we average. So those are physical quantities. That F is just a label, nothing else. It describes a region in the universe. Okay. Something else, yeah.
Yes.
Could you just try to clarify something, which is when we're talking about back propagation, you said that because of the
You're talking of, sorry, what?
back reaction.
Back reaction.
Back reaction. You said that there is a positive factor because of the co-evolution of two domains, but at different rates, right?
Yes.
So the question is back reaction of kind of feedback parameter between the domains or an interaction parameter?
No, nothing like that. There is no, in all these models, it assumes that these models are disjunct, their domains are disjunct. There is no flow of matter from one to the other.
Okay.
So if you take more complicated models, there is interaction, then you have to take into account shear. So some models also take into account. So for example, then this back reaction term also has the shear, which I said I just cancelled in the simplest time. So now this differential rates actually contribute to the back. Okay.
Those two domains are not affecting each other in any way, but,
No.
but their individual
Yes.
relation is affecting.
Exactly. From the next slide. So this is this bottom is cut off, but don't worry about that. So we are taking a very simple model, only two domains labeled by M and E, and individually these two domains are considered to be perfectly normal. Normal kind of physics happens like we see on Earth. I mean, no exotic dark energy and anything. So nothing, everything will have positive pressure. So the second derivative of the Hubble will always be negative, right? But because HM is different from HE, one may be higher. For example, empty domain may move at a faster rate expand. That is what you see. So this will be higher than this. So therefore, there will be a difference. Square of that is positive, and this will give a positive contribution. So if it can override, if this positive contribution can override individual negative AM and A double dot M, A double dot E, then you may have an overall positive for the global axis. That
Is this in line with time scale cosmology, where there's a similar idea that empty domains expand faster, and that is why we see this?
I see. I mean, I'm not exactly sure because I've not studied that aspect too much. But I mean, in spirit, you can call it similar, but maybe the physics may be different entirely. The microphysics or the origin maybe.
Thank you very much.
কোনটা?
Okay, we'll stop it now.
এইখানে যে ব্যাক রিঅ্যাকশন করেছি, এখানে ব্যাক রিঅ্যাকশন অবভিয়াসলি মানে তার ডার্ক ম্যাটার মডেল অনেক কিছু মাল্টিপল মডেল টডেল আছে। হ্যাঁ, সেইগুলো বেস করেছি, কনফিউশন আছেই আর ব্যাক রিঅ্যাকশনে যেরকম